Thank you, the organizers, for the invitation. It's really a pleasure to be here during this week. So for this mini course, I would like to speak about the rigorous derivations of effective models for suspension. So this will be the main topic of this course. So actually, this is a topic which has attracted a lot of attention in the last years and already in the early 19s. And I would like to give you an overview, a tentative to give you an overview about what are the main mathematical results. So I would like to switch between an historical overview of the literature, and also I would like to give you some ideas about the mathematical tools that have been used to obtain such a result. So let me maybe first explain what is a suspension. So how does it work? Yeah, with maybe some nice pictures. So a suspension means many particles that are immersed in an ambient fluid. So let me define this. So actually, you can think of a suspension as a flow which is constituted of two phases. So there is a discrete phase, which is the particles, as you can see on this picture. So the particles are assumed to be rigid, but as you can imagine, it corresponds either to bubbles or solids. And there is an ambient fluid, which we call a continuous phase. So the continuous phase might be a liquid or a gas, so the ambient fluid. And as you can imagine, there is a lot of applications of such a phenomena in different fields. So for instance, this picture comes from a paper by Batchelor and Nietzsche, and it represents sedimentation of blobs in a viscous flow. But I have another picture, for instance. As you can see, this is a spray, which is assumed to be, so we call this a thin spray, meaning that the volume fraction of the particles is really small. So there are lots of applications, let's say, for instance, in nature, when you think about sediments, in environments, when you think about clouds or dust, and also in medical fields, when you think about, for instance, blood or any biological fluid, such as many bacteria that are immersed in an ambient fluid. So the main idea, as you can imagine, is that when you want to model such a phenomena, you can try to describe the dynamics of each one of the particles using a system of ODs that you can couple to the equation of the fluid. So this means that we are looking at a microscopic description. So the particles are really small, and if you zoom in at a microscopic scaling, you can think of them as a discrete phase, so that it's a cloud constituted of many particles. But as you can imagine, this might be not relevant to describe the dynamic of each one of the particles, and one would be rather interested by having an average description of the suspension. So this means that we would like to have a macroscopic or a mesoscopic description of the phenomena. And actually, there are lots of models that are used in the physics literature, and this is what I will also talk about. So the main aim of this topic today is to try to justify the convergence from the microscopic model. So the aim is that we would like to derive some macroscopic or effective model starting from a microscopic description. And so what I wanted to say regarding this is that, for this introduction, I would rather just start to present to you the microscopic and the macroscopic and discuss about these two models before starting some more specific problems related to the homogenization of the Brinkman and the mean field limit. Okay, so just to not forget, feel free to interrupt me if you have some questions at any time. And before starting, I would like to advertise for some summer school which will take place in Bonn in the end of June. So I was planning to do it at the end of the mini course, but the deadline actually is close. So please tell me by the end of the day if you are interested by registering to this summer school that you are organizing. And what I would like also to emphasize is that we can also provide funding for young researchers for take care of the travel and accommodation. So let me know before the end of the day if you would like to register to this summer school in Bonn. So this is what I wanted to say for the advertisements. So now I would like just to give you more details about the summary of the introduction. So as I said, I will introduce first the, let's say, the microscopic model. Then I will talk about so maybe we can switch off because I will not, je ne vais pas en avoir besoin normalement. Yep. Sorry. Thanks. Yes, then I will talk about the macro. So the macroscopic model is a fluid-kinetic model, which is actually the Vlasov-Navier-Stokes equation. And then I would like first to give you a formal derivation. This will mainly allow me to introduce some tools that will be useful later when I will talk about the homogenization of the Brinkman and the mean field limit later on. So yes, let's start with the microscopic model. So I also like to call it rigid fluid by opposition to the macroscopic, which will be a fluid kinetic model. So as I said, when we zoom inside this suspension, what you have is many, let's say, spherical, for simplicity, identical particles that are immersed in an ambient fluid. So I will give myself n particles, and I will call them Bi. Is the ball centered in some position, xi having a radius r, so xi, well, I will mainly stick in 3 dimensions during this course, and r is the radius, which is supposed to be small. So n will be large, and the radius will be smaller, and I will precise the dependence between the radius and the n later on. So what you have to keep in mind is that this goes to 0 when n goes to infinity. Yes, so let's say that we are in a domain that I will call omega, which might be bounded or equal to the whole space. Okay, and so we will write the equation for the ambient fluid, which occupies omega minus the union of the balls. And this will be done by using a Navier-Stokes equation. So I will call un the velocity of the fluid at time t and position x. maybe I can. And I will call Pn the pressure. So the equation is the following one. So dTu n plus the non-linear term minus mu plus gradients of the pressure equal. Okay, I will write 0, but in general you can add some external force. We assume that the fluid is divergence free, and we prescribe a no-slip condition on the boundary of the balls, meaning that the velocity of the fluid matches the velocity of the particles. So un corresponds to the velocity of the particles, which are assumed to be rigid, which means that they only translate and rotate. So Vi is and omega I are the linear and angular velocities of the ith particle. So each one translates with some velocity and rotates. Okay. So this takes place on omega minus the union of the balls, closed. Okay, we also have some boundary condition on the boundary of the domain. Well, we will just assume that it's 0. So what I mean by the boundary of omega is the boundary if omega is bounded, or otherwise it's the limit when x tends to infinity. So this is the fluid equation. And then we couple this to a system of ODs describing the motion of the particles. So we will write a Newton law for each one. So maybe let me just precise the constant. So mu is the viscosity. Viscosity, rho f is the fluid density. And that's it for the moment. And F may be some possible external force. And then we couple this to the motion of the particles. So the motion of the particle is given by its velocity, and we write the Newton law for each one of the particles. So I will call the mass of the ith particle MP. So since the particle is spherical, it's given by this. So rho p is the particle density. So let me write this. And I will need more space for the next definition. So we have first the drag force applied by the fluid on the particles, which I will define. Let me define this here. So sigma is the Cauchy stress tensor. So it's twice the viscosity times the symmetric gradient of the velocity minus the pressure times the identity matrix in 3 dimensions. So du, so this is the stress tensor. Du is the symmetric gradient. Okay, so this is the drag force. And let me just check. N here is the unit normal pointing outward of the particle. So outward normal. Yes, so integrated over the boundary of the particle. And for instance, if you think about sedimentation, you need to add some other effect like gravity and buoyancy, and maybe some other things which might be also related to the force exerted on the fluid, but I would just keep it like this. And we do the same for the inertial term. So what you need here is the torque applied on the particle, which writes like this. Also on the boundary of its particle. Yes?
So, sorry, my question is, does it imply that you don't have overlap on the particles? Can you see it here?
Yeah, so I forgot. Bi does not intersect with Bj for I different from J. Yeah, so that's the problem is well posed.
But then, so when they touch each other, do you have like a reflection condition between the particles?
I mean, it's kind of problematic if they touch because, yeah, the model is not really, yeah. I mean, the whole problem of this course is that we will always try to avoid collision between the particles. This will come later, yeah.
Thank you. Sorry.
But yeah, thank you. I forgot to say that the particles does not overlap in this definition. So yes, let me just finish with the notation. So IP is the moment of inertia. In the case of a sphere, it's basically just given by this constant here. And I don't have space, but you also have to take some initial conditions for the velocities. So I will write it here. Xi and Vi at time 0 given initially. Okay. Yes, sorry. I forgot. There should be, no. Actually, we will quickly forget about the angular velocity for spherical particles because it doesn't really change anything in the limit model. But yeah, I mean, if we have time, I would like to speak about non-spherical particles at the very end of this course, but we are not there for the moment. So maybe no question. So given n fixed, and if the particle does not overlap, there are some results regarding well-posedness of such a system. And so I will just try to give you some references, but I will not really enter more in that in details regarding well-posedness. So maybe let's say many remarks. So well-posedness. There are some papers by Desjardins and Esteban. In 2000, in 99 and in 2000, so there are two papers. And I think they deal with weak solutions in bounded domains, so omega bounded. I think it's in 2 and 3 dimensions. And they prove, what they prove is a weak solutions. So local in time in the case of 3 dimensions, provided that the initial data are small and up to collision. So well-posedness up to collision is ensured. There is also a paper by Takeo Takahashi in 2003, I think, which deals with strong solutions. So this one is for strong solutions, also up to collision. And at my knowledge, the only paper where it is shown that actually there is no collision in finite time is the recent paper by Mathieu Hilleray and Lamis Sabah. So it's a paper from 2022. Yes. So they deal with the case of omega being the whole space, and they in 3 dimensions, and they prove that there is no collision. So well-posedness is ensured in a long time if the initial data are small enough, so no collision in finite can occur. Yes?
What type of solution is it?
So they don't specify it, but I think it's weak. And also they say that, I mean, if you have some nice initial condition, you can also expect strong solution. But the precise setting is not really described in the paper. So I think you can expect both when it's reasonable. And they deal with Stokes, but they say it works also for Navier-Stokes. Yes, so yeah, I will not really enter more in that. I mean, I will speak about the functional spaces when we will talk about, where I will present some more detailed theorems, but yeah, for the moment, I will just refer to this paper. I mean, there is a nice review of the previous results. There is also a paper by Feyreisel in the early 2000s also, but yeah, this is far from being exhaustive. So what I wanted to say, that's what I wanted to say on the microscopic model. So I will maybe give it a name.
Shouldn't there be a coupling between the vorticity and the angular velocity via coupled stress tensor there?
Sorry?
Shouldn't there be a coupling between the vorticity and which is the angular momentum, right, diffused in the fluid, and the angular velocity over there via coupled stress tensor? You only have the coupling with the Cauchy stress tensor. Why can you ignore the coupling via a coupled stress tensor?
Sorry, I didn't...
So in a fluid, you have also diffused angular momentum, right, which is the vorticity of the velocity. And you couple that with some sort of coupled stress tensor on every molecule, right?
Oh, sorry, on every?
So you're coupling the discrete inertia tensor with the discrete angular velocity, and then you have something which is essentially given by the Cauchy stress tensor, but then you should have also a coupling with a coupled stress tensor and the angular velocity of the fluid, right? Sorry, so the curl of the velocity of the fluid, no?
Yeah, I mean, the omega here is the curl of the velocity.
Of the fluid, or of
we prescribe continuity of the velocity of the fluid, which means that UN, this we will do it later, can be extended exactly by this rigid motion inside the ball. And when you do this, this means that VI is UN in xi, and omega I will be the curl of the, Yeah, so maybe I should have precise, I will talk about this when we will go further in details later, but yes, the idea is to extend the velocity inside the particle so that you have something which is defined everywhere in order to pass in the limit. But yeah, for the moment, n is fixed, and we are only looking at well-posedness. Okay, so yeah, I wanted to give a name to this model. I will call it rigid fluid, or let's say system N. So it depends on N. And so now let me present to you the limit model. I mean, one of the possible effective models, which will be the one if we assume somehow that the particles are quite dilute, meaning that the volume fraction of the particle will be small. So the fluid-kinetic model that we expect to get at the limit is the Vlasov-Navier-Stokes. So this means that I will still describe the fluid by its velocity and pressure. Of the fluid, whereas for the particles, I will rather describe them by a probability function, which gives you the. So let's define f of t x v being the probability of presence of particles at time t located in x and having a velocity v. So this is the probability b of presence of particles at time t, position x, and having velocity v. And so the Vlasov-Navier-Stokes, right? So we take the same Navier-Stokes equation, but then you couple it through the particles through a term here, which is the Brinkman force. So it should be a minus, or let's just put v minus u f dv. You integrate over all the particles. Mu. So it's proportional to the viscosity. Donc still the velocity is divergence free, and we have a Vlasov equation for f. Yeah, I will just keep this for the Vlasov-Navier-Stokes with some initial condition plus some boundary condition on omega. So this takes place in time cross omega, and this, and also there is a boundary condition for the velocity. So this I will call it Vlasov-Navier-Stokes. Yeah, thanks. So the boundary conditions, I mean, I will not really give you, I will not really talk about all the possible, let's say, version of this. I mean, there are many possible boundary conditions such as reflections or absorption. There are also some possible additional terms here that might pop up. There are also some models which are, let's say, more rich, so that you can add some Brownian effects, etc. But I will just focus on this one, and I will not really talk about well-posedness for this course, but maybe this will be tackled in some other talks. So here the density F is a probability function, and you have some nice kinetic energy which is satisfied for this system. And the aim of this course is to try to justify the convergence from the microscopic to this one. But I would like just to say some few words about this term here, which is the Brinkman force. So the Brinkman force has been introduced by Brinkman himself in 47. So actually, the idea was to try to give an intermediate model which describes porous media. So the idea was to introduce this term in order to describe something intermediate between Stokes and Darcy for porous media. And so in his paper, the idea was to introduce the following term, so something which is proportional to the viscosity. Kappa is the permeability times U. So mu is the viscosity. Kappa is the permeability. So that if the permeability is very big, you recover Stokes as if you're not in really a porous media. Whereas if the permeability is very small, you will recover Darcy. So this was the Brinkman term as it was introduced by Brinkman in his paper, and more generally we'll take such a formula. So it's something which measures actually the interaction between the particles and their effects on the fluid. So, yeah. So if there is no more questions, now I would like to give you a formal derivation of the Vlasov-Navier-Stokes starting from the microscopic system. How much time do I have? Okay, so well, I will try to write there. So So I will perform a lot of simplifications with some really formal arguments. So when you start, même si, ok. Sorry. So when you look at the fluid equation, one way to simplify the equation is to neglect the nonlinear term, or more precisely, the inertial effect. So this guy here. And usually, when you want to do such a thing, you need to justify that the inertial effects are negligible in front of the viscous effect. And this is done by considering the Reynolds number, which is a non-dimensional quantity which corresponds to this ratio. So the Reynolds, for those who are not familiar. So it's a non-dimensional quantity corresponding to the ratio between inertial forces and viscous forces. So the idea is that if you zoom in locally around each particle, due to the small length scale here, somehow the local Reynolds number will be small, which justify to neglect such a term locally around each particle, but such a simplification is not true anymore when you go further from the particles. But nevertheless, we can still perform such a non-dimensionalization in a specific setting, which is the case where the volume fraction is very small, and somehow justify the regime where you can approach the Navier-Stokes by the Stokes. But for sake of lightness, I will not do the non-dimensionalization today, but maybe I can refer to the nice paper by Richard Hofer where it is done. So up to one can perform a non-dimensionalization in order to justify the Stokes approximation. In a regime where the volume fraction of the particles is small. Fraction. So this means that from now on we will act like we have performed such a renormalization, and we will get rid of the inertial, the inertia of the fluid, where the volume fraction is small. So I refer to a paper by Richard Hofer from 2018, I think. Yes. Okay, so this is the first step. So we will somehow get rid of this guy. And next, the other key ingredient is to say, okay, now that I am focusing on what happens near each particle, if the minimal distance, let's say, is quite large between the particles, we can act like each one of them was not seeing the others. So the idea is to first try to study the problem when you have only one particle and try to say some few words about that. And then we try to use these specific solutions in order to approach our problem with a domain which is perforated with n particles. So let's focus on the problem around one particle. So I will erase here. So we will focus on one particle and neglect inertial effect. So this means we are considering a Stokes equation on the whole space minus one particle, spherical. So the setting is the following one. You have only one particle inside the fluid domain, which is the whole space. And we have just a Stokes equation. For simplicity, I will assume the particle to be centered in 0 and keep the radius. So I will call it B. So B is our spherical particle. And so still it is a rigid motion around, in the ball. And since you are in the whole space, we assume that the limit fluid velocity is 0. So here V and omega are given. Okay. And I put mu to be 1 because once you do the renormalization anyway, there is no more viscosity constant. So such a problem actually is well known, and it has been solved by Stokes himself. So he performed computations using the stream function and gives an explicit formula for this solution. But I mean, maybe I will give it to you later because anyway we will need this later on. But for the moment, let's skip the explicit solution. But what you have to notice is that it's something which decays like 1 over x, just like the fundamental solution of the Stokes equation that I will also recall later. And what is important is that he computed the Cauchy stress tensor on the boundary of the particle, and so here n is the inner normal. And he proves that it is given by the famous 6PR V times the Hausdorff measure on the sphere, which is renormalized. Yes, so V omega are fixed, and given. Yes, so this is the famous Stokes formula, which gives a link between. So once you integrate this over the sphere, you get an explicit formula for the drag force applied by the particle on the fluid or vice versa, which is the integral of sigma on the boundary is 6PR V. So here still n is the inner. And what I would like to emphasize is that the velocity here is the relative velocity of the particle with respect to the fluid velocity at infinity. This is important because we will, so here, V is the relative velocity of the particle with respect to the velocity of the fluid at infinity, which is taken to be 0 in this example, but it will not be the case in general. Okay. And what I wanted to say also is that now that we have computed the Cauchy stress, the normal components of the stress tensor, we can also see that if we extend the velocity by the rigid motion inside the ball, we get something which is continuous and well-defined. So U bar is in H1 dot, and its divergence is 0 in the whole space, and it solves the following Stokes equation. So you can prove that what you get here is exactly the jump of the Cauchy stress tensor, so that what you recover is this guy here. And this is on R3 with divergence 3. So here we are solving the equation on the whole space, so we don't see the particle anymore, and the effect of the particle is now given by this term in the right-hand side. Okay. We also have a formula for the torque. Let me. I think it's this one. So the torque is this guy here.
Is this equivalence, is it formal, or you can
No, it's
prove it
yes.
with this singular type of right-hand side, you match the exact solution?
Yes, I mean, since he computed explicitly the U, he also computed explicitly this guy and proves that it's given by the Hausdorff measure on the sphere. So what you get here is exactly the jump of the Cauchy stress tensor. So yeah, this is a true computation, right? And so for the torque, so I will call it T, which is this guy. Okay, maybe with a minus. This I never remember. I think it's, should be the reverse one. There is a formula which tells you that the torque applied by the fluid on the particle is given in terms of the angular velocity, just as the force, this is the drag force, is proportional to the linear velocity of the particle. actually the drag force and the torque. So maybe remark. The drag force and the torque are linear in terms of the velocity, right? I mean, this is linear in terms of u, and this also, so that we can prove that these are linear in terms of v and omega. And so since both are some vector constants, this means that you can construct a matrix which associates to each linear and angular velocity the associated drag force and torque. So this is a matrix which goes from R6 to R6. And this matrix will play an important role during this course, and it is called the Stokes resistance matrix. No, it's the inverse, sorry. So this is the mobility matrix. I mean, anyway, we will show that this is an invertible matrix, so I have drag and torque. And the computations of Stokes tells you that actually in the case of spheres, so you solve such a problem, the problem here, outside of a particle, which in general might not be spherical, and you try to compute the drag force and the torque given the linear and angular velocity of your particle. So this is the resistance matrix. And in the case of a sphere, it is a block diagonal matrix, right? Because F is 6PR V, and the torque is only proportional to the angular velocity in the case of a sphere. But in general, it's not the case. So I will call it R, the resistance matrix. So as you can see, it will be 6PR identity and 8PR identity in 3 dimensions. But in general, it's not true. What is always true, nevertheless, is that such a matrix is symmetric, definite, and positive. So R is symmetric, definite, and positive. And this we can prove easily. So I don't know if I have how much time. No. So how do you prove this? So I will consider the same resistance problem, which is the one on the top there, for some other velocities, linear and angular. I will call U prime, P prime, solving the very same equation. For some V prime and omega prime. No, so still on R3 minus the sphere for the same one. And what you can do is to multiply this equation by U, solving the other resistance problem. So I will call it star, so the very analogous problem for V and omega instead of V prime and omega prime, and you multiply, so 0 equal this guy against U on R3 minus the bulk. Since the velocities are all divergence free, actually you can prove that this is just the stress, the divergence of the stress against u, which allows you to perform an integration by parts so that you get minus sigma against gradient u plus a term on the boundary, which is sigma u prime, p prime, and u. Let me maybe precise what is this dot product for those who are not familiar. I don't know if everybody knows the meaning of this. So it's basically just the dot product for matrices. So you multiply all the components and you sum. But I didn't see that there is a third blackboard. And also I forgot to say, I mean, the pressure will not really play an important role. It will always correspond to the Lagrange multiplier associated with divergence-free conditions. So even when I will speak about well-posedness and the functional spaces for the velocities, we will always forget about what happens to the pressure anyway, because we always work with divergence-free velocity fields. So for two matrices, this is just the dot product, okay, for any two matrices. And so the product there corresponds to, so this is twice the symmetric gradients minus the pressure times the identity, the identity in 3 dimensions. Since u is divergence free, this guy doesn't contribute, so you get just twice the symmetric gradients of u prime against gradient u. And for symmetric reasons, this is the same as this or this. I mean, you can always put the symmetric on both sides, but nevertheless, minus p. I mean, we can also extend the velocities inside the particles and write the integral over the whole space, but nevertheless. So what do we get at the end? Yeah, so 0 equal this with a minus, so it gives you the gradient of u prime, gradient of u, equal to what happens on the boundary, which is sigma n u, and n here points outward of the fluid domain, which means inner unit normal in the particle, right? But then what we will use is that u is a rigid motion on the boundary. So this is just sigma u prime n times v plus omega cross x. And when you just compute this, I mean, this is a constant, so it gives you v dot the drag force u prime plus omega dot the torque. So now if I write this in terms of the drag forces, this is exactly v f prime drag plus omega torque prime, which we can write in terms of the resistance matrix as v omega, the resistance matrix applied to v prime omega prime. And then you see that the resistance matrix is symmetric, because if you just switch the rows, you get exactly the same because of symmetry of this dot product. It is definite also and positive, because if you take the same velocities, you get the energy which is positive, and it's vanishing if and only if the velocities here are 0. So R is invertible, and we call its inverse the mobility matrix. So this will be useful later, but maybe for the moment I will try to go a little bit faster in order to give you an idea about the formal derivation. So this will be useful later on. So let's go back to the formal derivation, and I erased the microscopic model. So the idea is that when you have many particles, what we will do is that if the particles are far away, you can always focus on what happens around each one. So we will call D, let's say, the minimal distance between particles, and assume that this is very larger than the radius. So the radius over D goes to 0, and D is also small anyway. So the idea is that when you solve the Navier-Stokes equation for the microscopic system, we will approach it by some specific solutions around each one of the particles. So let me make this more precise. So assume that you have a limit fluid. Let's say that UN admits a limit that we will call U infinity. Then formally, we will approach UN locally around each one of the particles, meaning on this annulus, so on the ball centered in xi with radius d minus the ith ball. I will approach it by this Stokes problem. So the very same equation with the very same rigid motion on the boundary of the ith particle, but what I will put on the boundary of the external annulus is the ambient fluid. So the ambient fluid, which we expect to be this guy, U infinity. So locally, we can approach what happens like this, but we can go further by simplifying this approximation by saying that since the minimal distance is quite larger than the radius, I can approach this solution on the annulus by the solution on R3 minus the ball, because the length here is quite big, actually. And also, since the minimal distance is small, I will approach U infinity by its value on xi. So we will go one step further. Or maybe I will do it. So for the moment, this is on the ball minus bi. So the idea is that I will approach let's say UN is close to the superposition of these specific solutions, where I will just write the same equation, but instead of working on the annulus, I will work on R3 minus the bi because of this. And so we will keep this condition anyway on the boundary of the particles. And I will just approach the value of U infinity around the exterior sphere by the value of u infinity inside, since these quantities are very small. But this is exactly the specific solutions that we call Stokes sets, actually. And these are explicit, actually, thanks to the computations of Stokes. And as I said, if we extend them by their value in the boundary, so let me put here on BI, meaning that this is their value on the boundary, you see that this guy will solve a Stokes equation, which is exactly this one, around each one of the particles with a sum, right? So VI bar solves minus Laplacian plus gradients equals 6 pi r VI minus, so here we need to take into account the relative velocity at the infinity. Yes, so this is the limit. Let's go to infinity. So here you have VI minus u infinity xi times the Hausdorff measure divided by its volume, right? Divergence equals 0. So this holds on R3. And now we are almost done, because if you sum over all the I, what you get is here a sum. And so maybe I can go. Yeah, we go there. So you see that we almost have the Brinkman term. So we need to do one step of simplification, that is to approach the Hausdorff measure by just the Dirac mass in the center of the particles. So in the sense of measures, this might be approached only by the Dirac mass, since the radius of the particle is small. So that the approximation is, so I will call it Vn solves minus Laplacian equal 6p r sum Vi minus u infinity Dirac in xi. And so I completely forgot about the inertial effects, but since we started from a renormalization, we should have here the Reynolds number types the inertial effect, but yeah, let's forget about this. And so now we are almost done, because if I define the empirical measure Fn, which is the sum of the Dirac's positions and the velocity, so this is a probability measure in R3 times R3, you can see that this guy here is exactly the Brinkman term, almost, I mean, so you multiply by n, and you divide by n, so that you get 6p r n integral of v minus u infinity Fn dv. Vn. Yeah. Okay. And so now formally, if you assume that such an empirical measure converges to the probability function of the distribution of the particles at the macroscopic scaling, and if Vn converges to u infinity, then you recover exactly, I mean, you recover the Brinkman force if you assume such a scaling. So this is the Brinkman scaling. You need to assume that the radius is like 1 over n in order to recover the Brinkman. So we are not done yet, because we need to derive the dynamics now. So I don't know how much that. Okay. So if Fn converges in the sense of measure to some f, And since un and vn both converge to some u infinity, you recover and if, let's say, Rn is equal to 1, V minus U. And I forgot about the small Reynolds number here. But all of this is formal anyway. Divergence equals 0. Okay. So now, if there is no question, we can continue with the dynamics of the particles. So for the moment, we are acting like the position, the velocities are fixed. But we need to tackle the dynamics. So I just recall here the system of ODs, which was this. Plus some gravitational force, for instance. And I forgot the J, I think, before. And as I said, we will forget about the talk anyway. Yeah, so I removed it. But actually, if you think about what happens to each particle if it was alone in the fluid, and you want to look at the stationary velocity, you will see that, so this guy is exactly the Brinkman, sorry, the Jack force. So you get an explicit formula for the terminal velocity of the sedimentation of one spherical particle in a viscous fluid, whereas the torque, which is given in terms of the angular velocity here, tells you that the terminal angular velocity is 0. So this means actually that we will neglect anyway the effect of the torque and forget about what happens to the rotation of the particles since they are spherical. And so thanks to our approximation, this one, this guy here, Vn, we know that this term is actually, again, the Jack force there. So this is, and since here n is the outer, this should be minus 6pr Vi minus u infinity xi. So up to a normalization, what you find is that the system of ODs is something like this. Okay, so you need to take into account a renormalization, but I didn't do it here, so what you get is OF PJ. You get something like this, but up to a renormalization. And then we are happy because we can prove that Fn satisfies, in the weak sense, a Vlasov type equation. So if, let me maybe give this a name because, I mean, there should be a renormalization anyway, so these are not really the constant that should appear. But so Fn solves something like dt Fn plus V gradient x Fn plus divergence V. And then you get u infinity minus V with some constant plus the gravitational effect. So let me So this is easy to prove. I mean, if you look at the weak formulation satisfied by the probability measure Fn, you just can plug it inside these two systems of ODs, and you see that it indeed satisfies such a Vlasov equation. And so Fn. And so naturally, if now you assume that Fn goes to some probability measure, you will naturally have some limit Vlasov equation, but provided that you have the right constants up to renormalization, which I didn't do here. So this is the formal derivation. I don't know if I forgot to say some things. Yeah, so if Fn converges to F, we recover a Vlasov-Navier-Stokes with Vlasov-Navier-Stokes with a gravitational term, actually, which comes from the gravitational effect that we put at the beginning, actually. Yeah, so I don't know if there are some questions or. Yep.
Could you elaborate on this approximation that you did in the dynamic of the particles, in which you replaced the force, which is coming from the stress tensor, by this evaluation?
Yes, so UN is almost like this guy. And this naturally gives you that its drag force is the one coming from this term for I. Yeah, so we use that Vn is always close to, sorry, Un is close to this Vn.
So it's yet another approximation.
Yeah, I mean, it's the same that we used before, somehow. Yeah. But so this idea of approaching what happens locally inside each particle will be always the same. I mean, that's why I wanted to introduce the specific solution to the Stokes equation around one particle, because it will be very useful later. We call them the Stokeslets. So yeah, maybe this would be important later. And as you can see, this also suggests that such a model is what you get when you have spherical particles, because otherwise the Brinkman term will be more complicated. Because, I mean, what we use here is that the resistance matrix for the spheres were block diagonal with these explicit forms. So maybe I will not start now the second part, where I will talk about the Brinkman, the derivation of the Brinkman term, but maybe I can just give you the main idea of about the historical overview. So as you saw, this has been done in two steps. The first step was to freeze the motion of the particles. So what happens in the literature is that most of people just consider the fluid equation with freezed particles. That was the idea, and try to pass in the limit only in the fluid equation when the number of particles tends to infinity. And this is equivalent to performing a homogenization on a perforated domain. So this will be the main first part of the mini course, the next so the next time. And then once you have an idea about the limit velocity, you can plug it inside the dynamics of the particles in order to guess a transport or a Vlasov type equation for the motion of the particles. So it will be done in two steps. So the next time I will talk about the derivation of the Brinkman term, this one. I will try to give you an overview of the history and also a slightly more rigorous proof, but I will not really enter really in details. I mean, otherwise it will be too long. And then in the last part of this talk, I will speak about the derivation of some evolutionary equation, and I will mainly stick with the inertialess system, so the one where you neglect both fluid and particles inertia. So maybe, yeah, that was 10 minutes. I mean, I could start the next, but maybe it's better to.
Now, so that we have some time for questions before going to lunch. So, are there questions?
Thank you very much. I was just wondering, so the term which is collinear to G, the 4/3 pi R3, this one goes to 0 even after renormalization as n goes to infinity?
So you divide it by this one,
Yeah.
which is 4/3 PR3. So it's the same here. I mean,
Okay.
but actually, after renormalization, this one gives you something here. When you renormalize the velocity, this I didn't do. That's why I was saying that this guy might not be exactly actually this one. And actually, you also somehow renormalize the radius in order to work on a length scale where the motion of the velocity evolves, but it's something of order 1. So these guys will always scale in the same way. Ah, no, sorry, but this one, no, because we also rescale the velocity of the particles. So yeah, you're right. These will not scale in the same way also after renormalization.
Because the stress tensor is scaled in R to the 1, or is
R to the 1.
this 6 pi R?
Ah, yeah,
Maybe,
this
yeah,
one. I mean, the renormalization, you do it before approaching UN, so you get here something, I mean, I don't know exactly the scaling which appears here, but it's not really R, I mean,
Okay.
before.
And they scaled.
Yeah, there is a, yeah. So if you are interested by this, I can refer to you to the nice paper by Richard Hofer of 2018, which the renormalization is done in details, so that you can see the scaling of each term.
Any other questions? Then we can thank Amina